and so let's go to RStudio, and whenever you have to leave, just leave. I mean, we'll continue. Um, so um, until now we have given so uh, so probability theory is like gives a sense to the distribution of let's say we have some data, and probability theory gives a meaning to the distribution of this data. I mean, this is it's a formal meaning, and I mean it's defined, but in real world we have the data in statistics. We have the data, and we don't know the distribution of them. So probability is just the language that we use and with which we define things. So mm, how does it work? All what we have said on testing, on linear regressions. Well, we have a model of the world, like we start with a model of the data of the world, with which we look at the data. And then, as a second step, we try to infer something from the data to our model. So this model can be linear regression, where beta 0 and beta 1 can vary. I mean, we first fix the model that the y variable is equal to beta 0 plus beta 1 x, the x variable, and then we try to infer the coefficients beta 0 and beta 1. So let me give some examples that, like the first one can be like a discrete example, which is, for instance, the example we already did, like there are two variants of the same word, one dialectal and the other one formal. So we already discussed this model. The model is the following: is that a person tosses a coin of parameter P to choose the variant of the word, independently one from another. This is fundamental. So this is a model, and how do we formally say how? Well, the model is, for instance, we can choose the probability measure with which, like, let's call 0 equal to the formal variant, 1 equal to the dialectal variant, and let the participant to the experiment, or let's observe, don't know, 3 times the word. So and record the variant used. So the probability is the one, I don't know, with this model, what is the probability of looking at at this sequence, for instance? Is the usual Bernoulli trials, like the first word is formal, the first variant is formal, in the second observation the variant is dialectal, and in the third observation the variant is dialectal. So the probability, what is the probability of this sequence? Do you remember it?
The probability of this sequence.
Yes, for instance, so you told the model is that I don't know, in the experiment, for instance, maybe we are seeing a text of an author and we see 3 times this word which can have these two variants. And the model is that when the writer wants to write this word, he tosses a coin and decides the variant. So it's not a really sophisticated model.
Probability is 1/8 because it's 1/2 to the power of 3.
Yes, but the coin can be not fair because it's a parameter p. So it is like p to the power 2 because there are two ones times 1 minus p, for instance. So our model here is the following. Is like this set of probability measures, which depend on p, where p is between 0 and 1. And these probability measures are the usual of the Bernoulli trials, the usual ones that we have seen many times. So the probability is like the probability of tossing k times a coin of parameter p. So x1 equal to, I don't know, 1, x2 equal to 0, x3 equal to 0, for instance, is equal to 1 minus p to the, let's put also an x4 equal to 0. This is equal to 1 minus p to the power 3, because there are 3 zeros, times p. So we can compute the probabilities of every sequence for every p. And this is our model of the world. It's not really sophisticated because, I mean, but it's a model. Then, okay, this was an example of a model. Then we can do an example of another model, like a continuous model. For instance, we have x, a random variable, distributed a random number, so a number that is observed, I don't know, k times. So and let's call the observations x1, xk. So a possible model is that a possible model and used model is that the xi's are independent and distributed as a Gaussian. So what is the Gaussian distribution? Is that the probability that xc is in an interval and b is equal to this formula. I mean, you don't know, you don't need to know it by heart because on Wikipedia is the first thing. I mean, it's really easy to look for this formula. It's really famous. So is the integral uh, of this expression here on the interval AB. So I mean, this is a definition, but you see there are two degrees of freedom, mu and sigma, which are not fixed. So I mean, this is a possible model for this exercise. And the independence, what does it mean? That, for instance, it means this stuff here that, so let's put, since this depends on mu and sigma, let's keep it in the notation. So, and mu and sigma are, mu is is an element of R, is a real, and sigma has to be positive. So independence, what does it mean in this case? That if we want to compute the probability of a sequence of, I mean, of a, not of a sequence, of k observations, we need uh, to factorize this expression here. So let's assume that we observed all these values for xk. Well, so we want to compute this probability here. So what do we do? Like the independence, what does it mean here? That we can factorize, like the independence means that we can do this product. does it make sense? It's like, do you remember that there is another formula which is always valid, that we first compute this first probability of x1, then we compute the second probability conditioned on the first appearance, but then we use the independence, and we can say that x2 in this interval, given that x1 is in this interval, is equal to the probability that x2 is this in the interval a2, b2, given that x1 is in the interval a1, b1, is the same as the probability that x2 is in a2, b2 without the conditioning event. So, I mean, this is the definition of independence. We have seen it in the class. And then we can use like this expression here. So I copy and paste it k times. And substitute A with A1, B with B1, and the last A with AK with, and B with BK. So I can compute the probability of what I see. If I knew mu and sigma, so I don't know them. So here the model is the following family of probability measures. Uh, mu, where mu is an element of the real numbers, and sigma is a positive number. So this is the model in this case. Like, it's a family of probability measures that we assume that our data follow. Many times we do it because we need to do some assumptions, but we need to start from a point. So I mean, maybe it is not so satisfactory, but there are also models which are more complicated. I don't know if you remember, but in the probability lecture notes, I spoken about like a work. I mean, there is this Markov chains which are really used now, in science today, but actually they have a linguistic origin, because this Markov was a mathematician and was trying to see whether, like, the appearance of vowels and consonants in the Eugen Onegin, like, followed the Bernoulli trials, or maybe there was the independence hypothesis was not satisfied. And he found, of course, that the independence hypothesis was not satisfied, because I mean, he made a test, and he saw that uh, it is highly unlikely that the Eugen Onegin is the consonants and the vowels in the Eugen Onegin are chosen tossing a coin. So, for instance, and but he made also other models which are called Markov models, which are more sophisticated. And I guess used also by this generating, I mean, they're quite used also, I guess, in computational linguistics. But okay, this is not the point of today's lecture. So now, what's then this is a general remark. Now, the thing to say is the following, which is that now we want there is the inference part, which is where statistics enters. I mean, where not where statistics enters also in defining the model. But the inference part is how to estimate p, and in the first example, and mu sigma in the second. So this is the question. Now, in the case of P, we have seen that like the mean is a good estimator. I mean, we use like this central, not the central limit theorem, the law of large numbers. We made some examples, but now we are in a Bayesian setting. I wanted to tell you about the Bayesian setting. That is, even if we estimate p, for instance, in the first case, even if we estimate p with an estimator, I don't know, with hat p, which can be, for instance, the sum. Sorry, not the average. So this is equal to the fraction of variance, of the dialectal variance with respect to the total. This estimator is still random, because if we let the writer write another time the word, this will change. So in the Bayesian setting, also p is random. Maybe I should explain it better, because it actually makes sense pretty much also in statistics, because when you want to compute like a probability, you usually take a corpus and you compute some statistic. But a corpus, there is not only a way to collect data. A corpus gives you a good idea of many things, but it can be, I mean, there are some choices to be made, this P maybe doesn't even exist, but you use it because it is useful for computations. And in the Bayesian theory, the probability theory, a probability has the meaning of likelihood. So in the P, sorry, has the meaning of like degree of belief, degree. So if you observe in a large corpora, for instance, on the uh, on a Russian dictionary, uh, like all the verbs, you take the fraction of all the verbs divided by over all the words. But maybe if you take another dictionary, this fraction will change. Uh, I mean, this definition of this point of view of probability is much more flexible, and for things that are not physics, it's better. It's so in practice, you can have beliefs on everything. So you can put, you can compute the probability of, for instance, of p. I don't know if this makes sense because, for instance, you can compute the probability of p, meaning, so for instance, you can compute, for instance, this quantity here. The probability that p is in 0.2 and 0.3. This is equal to the degree of belief that the coin that the author tosses has parameter p in 0.2 and 0.3. So I'm simply rewriting what I mean for the left-hand side. So computing these quantities makes sense because basically if you don't know something, you can regard it as random. You don't know p, you can regard it as random. So the ingredients for the Bayesian statistics are the following. So one is the prior, sorry, which is your before observing the data, you have some belief on the model, some beliefs. For instance, I don't know, let's take coin tosses. You could have this kind of prior probability, like let me go to, let me write something. Pick up the pen. Okay, now I would do it. So for instance, now I take a coin from my pocket and I toss it. But before doing that, maybe you have, I don't know, here there is one half. Usually coins have one half probability of falling into one head or one half into the other one. So it will be the maximum. This is the probability. Here on the y-axis, we put the probability that P is in the y, sorry, in the x, divided by the x, actually. So it's a density. And maybe your prior knowledge tells you that you most likely, or maybe we can even be more sharp, and you really think that the coin that I have in the pocket, yes, maybe we can also say that you think, okay, so this prior is not really interesting. So you think that the probability that P is equal to 1/2 is equal to 1. This is one possible prior. But it's not really interesting because, I mean, maybe there is the possibility of doing coins that, I mean, maybe it's a little bit bounded, the coin or everything. I could drag it. So maybe it is better to take this kind of prior, like this one. So you really believe that is the money has more or less 1/2 and 1/2 probability to fall in every side. So, but you still there is the possibility of seeing other. Maybe you don't really believe that it could be like 0.9, but maybe if there can exist such a coin. This means so once we fix the prior, which is the degrees, I mean, your beliefs on the model. Then we look at the data. And three, we update our beliefs. So this is we update our beliefs because now we undercompute the posterior distribution. So we are interested now in this object. So the probability that so our beliefs on the model given the data that we observed. So does it make sense? So now we observe some data, our beliefs change. And how do they change? Well, according to the Bayes formula. So let me do an example. So the posterior distribution is obtained with the Bayes formula. So we are interested in this object and this is equal to the probability that of the data given okay, let me okay, I was taking a discrete example simply to avoid this issue. So let me take a precise example, and let me first do an example, which is the following. So, mm, and then I will write the Bayes formula. So, coin tosses. So, we take the following prior. The probability that P is equal to 1/2 is equal to 0.9, and the probability that P is equal to I don't know, 0.9 or 1 is equal to 0.1. So what does it mean? It means that with high probability, you believe that P is equal to 1/2, that the coin is fair. Does it make sense? Okay. So now you observe a head. So a 1. How do so you observe a 1. Now what is the let's do this exercise. So let's compute the posterior. So the probability that P is equal to 1/2 given the data. So given that we obtained a 1. So how would we do this? I mean, here we can do it by graphical inspection. So like mm, it's I mean, first of all, do you get what we are doing? So like okay, then it's actually here there is really easy to do it because
The probability is 1/2. Like we tossed the coin once and it gave us head. So we can either think that no. So the only other so we could have gotten a 0 or a 1, and is it actually any different from the initial probability? Because like one toss doesn't give us anything, I think.
sorry, I don't listen. Well, I close the door because I'm not listening so well. So, okay. I didn't get what you said.
Sorry, yeah. So I was thinking that one toss wasn't enough for us to change the probability. Like,
In the test, you mean in the test? Test. If we were make, I mean, because now we want to compute this probability. And you mean that in the tests that we did in the beginning of the classes, one toss was not sufficient to make us reject that the coin is fair in favor of the coin is completely rugged.
well, kind of, but do I understand correctly that P is the probability of getting ahead?
Yes, yes.
Then if we got ahead, probably probability that P is that small p is equal to 1/2 would decrease slightly.
That's correct. That's correct. In fact, we can compute it quite. Not is not released in this case. We can, for instance, so here is the event in which the probability is equal to 1/2, and this event has probability 0.9, has this degree of belief.
Sorry, the screen is mostly black
Sorry.
and there's just it glitched a little bit.
So there are two possibilities, either that p is equal to 1/2 or that p is equal to 1. That p is equal to 1/2 happens with 0.9 degree of belief, and p is equal to 1 with 0.1. Then, in each case, we toss a coin. Here we have, well, for the definition of p, we have 1/2 can be 1 or it can be 0, and both with probability 1/2. So in this case, the output is 1. In this case, is 0. And here, instead, when we toss the coin, for the definition of P, we have that with probability, sorry, maybe let me write head instead of 1 and 0. So head and tails. We have head with probability 1 and tail with probability 0. Then here we have head, head, tail, tail. And we observe like head. So we are either here or either here. Well, this happens with probability 1/2 times 1/2. So 1/4. This happens with sorry, no, what?
With probability 1.45, right?
Yes, yes, 0.45. And this happens with probability 0.1. So the conditional probability is like a proportion. So we need to take, this is the probability that p is equal to 1/2, so that we are here. Is equal to 0.45 divided by the total number of possibilities. So 0.45 plus 0.1. Um, so yes, this is the and this is equal to, it's a little bit less than 0.9. Let's see, we have a wonderful computational, we are working, I'm basically typing on RStudio, so, but it has also a console, so I can do it here, the computation, 0.45 divided by 0.45 plus 0.1, which is, as you said, a little bit less than 0.9. So your probability, you believe a little bit more than maybe it's rugged the coin, but still it is more probable that it is not rugged because that it is fair. So this is equal to 0.8. So yes, in this case was really easy. In other cases, um, so uh, assume we look, we observe the sequence. Um, yes, the sequence 0, 1, 0, 0. We want to compute this probability that p is equal to 1 given this sequence. So the p is equal to, I don't, uh, okay, should pass to the densities, but let me use an equality sign here, that p is equal to a certain number, I don't know, theta, or let me call A, given this sequence is equal to the probability that P is equal to that I get this sequence, given that P is equal to A, divided by the probability that P is equal to A. This is the Bayes rule. Ah, no, sorry. what I'm saying. Here is the following. The following is the Bayes rule. So the probability of finding this sequence. So it is this one, the Bayes rule. Okay, so now we have what was my plan for the lecture is what is my plan for the lecture is to discuss about this expression. So I want to recognize here two objects. The first one is the tree. We have already introduced it because you see there is here there is the prior, which is the probability that P is equal to A. Then there is this other expression, I write it in bigger, in capital letters. So there is the prior, which we have already introduced. There is this function here, which we will call likelihood, and we will now do, I will say more about likelihood. And then there is something dividing. This thing that is dividing is really not essential. Why? Well, I will make it clear later, but actually you can see it also now if you have some experience with probability, because on the left-hand side you have a probability. So the denominator is not really essential, since on the left-hand side we have a probability that is that the integral, no, mathematically I'm writing it very badly, but this means that the probability that P is equal to A given 0, 1, 0, 1, for instance, for this sequence, integrated where A goes from 0 to 1, so summing all these possibilities in dA, this is equal to 1. Because we know for sure that P is between 0 and 1. So this is equal to the probability that P is in 0 and 1 given this sequence. So actually this is written awfully mathematically in the left-hand side. It should be like, now I'm confusing the density with the probability. So this should be, but it's just to tell you that now if I integrate also the right-hand side, the denominator does not depend on A. And it is therefore only a normalizing function coefficient. Uh, and the interesting part is on the numerator. So this is what I want to do today, and then I will. So today I will introduce the likelihood, and then introduce introduce a Bayesian linear regression in R, which is done with the with the package uh, Bayesian random model, I guess BRMS. So this is the plan for today. Um, now, mm, okay, let me. Uh, okay. So the likelihood function. Yes, then I will also say better what I mean, use the likelihood function in Bayes formula. So actually, it's quite easy. Let's start with an example. Assume that our model is the following. We have a variable x, a number that can take the following probabilities. That can be equal to 0 with probability theta. Then can be like 1 with probability, again, theta. And then it can be 2 with probability 1 minus 2 theta. And we observe, for instance, 0, 2. So our model, so we observe some data. And we assume that the xi's are independent and identically distributed. So what is the probability? So our model is actually a p theta, so I will put it in the notation. Well, for this outcome, why doesn't okay, for this outcome, what is the likelihood? The following is simply defined as the function is the function of theta that associate to theta the probability uh, of seeing that output is this function. So nothing more and nothing. So you observe the data, you have your model, and the likelihood function is the probability is how much the model with this parameter uh, is a function of the parameter of the model, and it gives is the meaning is that how much the outcome that you see is probable under where the probability is I mean is computed in theta. So in this case, could you compute it? I mean, it's let's call it L theta, this function. So L theta in this case is equal to the probability that x1 is equal to 0 times the probability is equal that x2 is equal to 2 because of independence, and then this is equal because of my definition to theta to the power of 2 times 1 minus 2 theta. So does it make sense?
I don't really understand why the first. Why is it squared?
Ah, you're right. Okay, then you understand it better than me because you're right and there is no square. Um, and okay, in the general definition of likelihood is the following. Is so we have a model. So let P theta be a model of the world. So, for instance, in the examples we have seen that theta could be equal to P for the linguistic example. or that theta can be equal to this mu and sigma in the second example, continuous example. So given this model, the likelihood of t and given let v omega be some observed data, the likelihood of omega is a function of the parameters of the model, which is equal to the probability that of omega given t. So I mean, it's nothing. It's just a definition. So we fix the outcome and we make the model vary. So it's nothing deep actually.
Sorry, yeah, I have to go, unfortunately.
Okay.
But Luba is here.
Mm,
Yeah, see you then.
see you. Have a nice seminar.
Thank you.
Okay, so I mean this is okay. Now so let's do one more example of likelihood. Which is in the Bernoulli trial. I mean, always the same measure. So let's toss. I don't want to repeat again the linguistic example, but I will speak about coin tosses. So let's take I don't know, like 5 coin tosses. With a coin that has parameter p. We observe, I don't know, the following sequence: head, head, tail, head, and head. What is the likelihood of this? What is the likelihood of this output? Well, do you remember the like the measure of Bernoulli trials? So this measure is the following: the probability that so first the model is the following. In this case, I've already said it, but I will repeat it. Is the following family of probability measures. So we assume that the data is distributes according to one of these probabilities. And here the probabilities are defined in this way. For instance, I don't know, instead of giving a general definition, let me give you an example. So if I observe heads, and tails, then this will be p to the power of 2, because we have two heads, times 1 minus p. This is the probability of this sequence. And we can compute in the same way the probability of every sequence. So this gives me a whole family of possible distributions. The sequence HTHH has been drawn according to one of these definitions, of these probabilities. Which one is it's a question of inference. So let's compute the likelihood. The likelihood of this event is simply LP, which is equal to the probability that this probability measure, P parameterized by P, has this outcome. Well, but this is exactly what I wrote before. So above, we have 4 heads. So there is a P to the power of 4 times 1 minus P. So is it clear, this measure, and how I compute it? I mean, it's this is a Bernoulli trial, and we can also plot it with Wolfram alpha. So I go here. I can compute this likelihood, which is P to the power 4 times 1 minus P. And you see, it is this function here. So near 0, if P is equal to 0, well, it is impossible to find that outcome, because the only possible outcome would be 5 tails. If P is equal to 1, the only possible outcome are 5 heads. In the middle, it is possible to find all the outcomes, and yeah, this is the likelihood. I mean, from P that goes from 0 to 1. So this is the likelihood function. And now we come back to the Bayes formula. So the Bayes formula tells us that we have, given a prior, a prior, so our beliefs that is, given our beliefs on the word before looking at the data, given the likelihood of the out given an observed outcome, then we can compute the posterior probability. So given an observed outcome and its associated likelihood, and compute the posterior probability, which is the thing that we want. So let me give some formulas. So if the model is the following, then the observed data is omega, and its likelihood is L theta equal to P, the probability of looking at it, of observing it, if the actual probability is given by theta. Then and the prior is, we have some prior, sorry. Let's say theta, these are the probabilities, I mean, is the degree of belief of that the data is drawn from a distribution with theta, which is in AB, let's say. This is equal to, say, I don't know, let's call it little, the integral between A and B of little p of theta, the theta. Let's say we have some continuous prior. Then the Bayes formula is the following. Define P of theta given omega, the observed data, as the density of what we want to compute, which is the probability that theta is in AB. So after we compute, after we observe the data omega. That is, the probability that theta is in AB given the observation of omega is equal to the integral between A to B of this function here. This is the definition of this p theta given omega. The Bayes formula is the following. I mean, it's a little bit complicated because I passed from a prior which was discrete to a prior that now is continuous, but the Bayes formula still continues to hold and is of the following form. Like it is the following. The probability that theta, sorry, the density theta given omega is equal to the probability of omega given theta times the prior density divided by so this is the Bayes formula for the densities. Is equal to divided by the probability of observing omega. So, and we can recognize here the likelihood. So this is equal to 1 divided by something that does not depend on theta times the likelihood of theta times the prior. So this is the Bayes update rule. So the idea of the Bayesian statistics is then that okay, you fix your possible model. Let's say you fix, I don't know, that your author when writing a word tosses a coin to decide which variant you want to use. So in advance you give I mean you restrict to, so you have to have something in mind. Then, with that in mind, you observe your data, and then you can do inference. So, for instance, the author tosses a coin, but you don't know the parameter of the coin or whatever. There are still some incognitas. when you observe the data, you can say something on these remaining incognitas. And in this case, the Bayesian statistics, however, regards those incognitas as random variables because you don't know them. And if you don't know them, they are random for you. So, I mean, maybe your prior for a coin toss is really, really centered around one half. However, if you see five heads in a row, maybe you start thinking that the coin can be rigged. So, but there is like this rigorous rule of updating, which I have written it here, which is the correct way of updating your beliefs after you observe the data. And so basically, we can write like a graph here. Here you have, for instance, in coin tosses, your belief is that the coin is really, really, really centered around, I mean, you believe that it is the parameter of the coin is one half, that the coin is fair. Here I'm plotting in black P of theta, our prior. Then I'm plotting in red, then I've said like this output, head, 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 for instance, and tail. Now, this output, what is the likelihood of this output? Well, it is sharply peaked near 1. It is peaked near actually 1/6, here, like. So here I'm writing the likelihood of the second output. Now, to update it, what do I have to do? Well, I have to multiply these two functions and then dividing it by a constant. So p theta given h, 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 and t will be equal to 1 divided by c, the product of the likelihood of theta, of this output under theta, times our prior. And yes, and uh, uh, sorry, uh, uh, was I? Yes, what we obtain is something that is uh, the output will be in green. I write this in green, and it will be something in between the two functions. So it will be something like here. This will be my posterior. and I mean, this is the right way to update the 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 things. So um, I mean, it was this ends the theoretical part of it. I mean, it has been I made it the last day, but it actually gives like a more rigorous framework. Is more rigorous than testing because testing is like I mean this is purely mathematical. So it's all defined. You have to have a prior. The problem is what prior do you use? I don't know. It depends. But once, I mean, the things that we don't know precisely what to put are really well defined. So, like the prior is an object well defined, and we know that there is the problem. And we can there is nothing we can do. The prior is something that we have to in most of the cases put an acceptable prior, but after we put it, we know the update rule. So everything is rigorous. Instead, with testing, we don't really know what uh, is, sorry, we don't really know what I mean, it was more like, okay, we take this p-value, and for some reason, if this p-value is smaller than here instead, we can do this is more, I mean, much more explicit, this construction. That's why I wanted to do it. And now I want to pass to the part of practice in which I wanted to show the this Bayesian linear regression. So the package you have to we have to download and to install is the following. It's called bias guess random mode RML. Che have already installed it. No, so MRS, sorry. I don't know actually what does it mean, so let me. It stands for Bayesian regression models using STAN. STAN is a C++ package for obtaining, so it is a code that works passing through C++. And well, let's see some data like The data we will work with is the following. Uh, sorry. So is some data. Uh, let's look at it. So it's about if I remember correctly, it's about the pitch. So like the frequency of words pronounced by different subjects in different contexts, in different sentences, by and the subjects are of different sex. We want to see if the pitch depends like on the context or on the gender. So let's first plot it. So let's plot uh, let's plot um, so, with a box plot, for instance. So we want to plot the pitch. So y will be the pitch. X will be, for instance, the context. And let's put also the gender. And let's see that there is some difference because you see the pitch depends a lot between the gender. It is if the participant is a female or a male. Then also depends on the it seems to depend on the context, even if a little bit less. But so we want to predict the pitch using the context and the gender. So we want to do the following model. Uh, is equal to uh, beta 0 plus beta 1. Uh, this is the dummy encoding for the context variable plus beta 2. Since these are categorical variables, we need a dummy encoding. So D will be equal, the context will be equal to 1 if the context is informal, 0 if it is equal to pol, which means, I guess, polite probably, or I don't know, I don't know, the converse of informal, I guess, so formal. And the gender would be equal to 1 if the participant is uh, male or female, and 0 vice versa. So this is the usual regression model, and we can do it with this Bayesian approach. So in the Bayesian approach, let me first see, run the code. So let's feed it with BRM. We want to predict the pitch using the gender and the context, and the data is equal to the F. So it takes some time to compile. So basically, in the Bayesian approach, everything is random, and also these beta zeros, beta 1, and beta 2. What will do this program, and then I will tell you how, is to compute the posterior distribution of these beta zeros and beta 1. Now, after we observe, well, the data that we observe. So, so the data that we observe is this def that we put, we feed with which we feed the function. Then this Bayesian function will give me a distribution instead of fixed values for beta 0 and beta 1 and beta 2. There will be a distribution, and now briefly it will give us an output. So now I will start writing the code. So the output, we will summarize the output, the summary function, and then we will see the values of the posterior distribution with this function sample posterior, sample probably. How was it? I don't remember it. What? So posterior samples of fit, and we save them into. Okay. It gave us an output. A lot of computational indications, and then we can summarize the model. So you see the intercept, the beta 2 and the beta 3 have some estimates, have some data, and we can look at this posterior sample. So you see here we can also this gives us the samples for beta 0, beta 1, and beta 2. So we can also plot an histogram with them. So for instance, we can plot, so let me save the output of these posterior samples into posterior distribution. So, and we can plot the histogram. I don't know, we can plot the posterior distribution for the coefficient of the context. Have to run again this code. And then I have to I can plot this histogram that maybe be plot as hist. Yes, and you see the posterior is centered at around -20. So maybe if we were to run a linear model, it would have given us like -20, something like that. But here, the Bayesian model gives us a posterior distribution, not a fixed estimation. And there is another point that this function can that we can change. Well, we can change the prior because I didn't speak about prior, but this what are the prior for these beta zeros and beta ones? Uh, well, they are like uniform ones. So there is no before running this function, you have no like you have no there is no favorable outcome. You have your knowledge is completely is zero about them, so you would rather say that beta zero can take whatever value with the same probability. Beta one the same and beta two the same. So, but we can put like other other priors with this command, like we can put a normal run, a normal prior. Uh, so we have to run this function DRM. We want to predict the pitch using the gender and the context. And we can put prior equal to I don't remember quite the prior. Well, I think I have it here. So uh, set prior, okay. And we take a normal of parameters 0 and 5. And class equal to B. With this command, we will do the same thing, but now we are taking like a prior which is really concentrated around 0, much more than before. So now, what do you think it will happen if instead of taking a spread, I mean, what do you think? Well, I would say that this histogram will shift near 0 because now you really believe much more than before that your betas are near 0. So because of some reason, because of your prior, and you can give this information to the command using this set prior. Well, so the idea is that now this histogram will shift to the right. So I can simply start writing the code. In the meantime, that this BRM will do its job. So we want to sample from the posterior. So posterior sample for this new normal model, and we want to take the column which corresponds to the context pole, and we want to take the histogram. And see the difference with the one that there was before. So we have simply to wait for this function to fit. Then, for the last part of the lecture, I will explain how this function works. Okay, starting sampling. So it will be finished now. Okay, well, now we can run this code and see that the histogram now um, yeah, beacon. So you see now this histogram is actually more, I mean, centered around zero. It's more because our prior was more gave more weight to zero. So now, how does it work? This command? Well, this command works in the following way. Uh, so we actually it's complicated, but the idea is the following. Let's try to. So we made before the example that we had this coin, that we had these beliefs. We had the following prior. Uh, so I strongly believe that it is a fair coin, so the probability that P is equal to 1/2 is equal to 0.9, but there is a possibility that I'm ditching you and I have a coin with two faces or two heads or whatever that always ends up in head, and this can happen with probability 0.1. So this is my prior. Now I observe one head and I obtain the following posteriors, which we computed like before. Which is the probability that P is equal to 1/2 is equal to given that given a head. So now I observe a head. This is equal to 0.45 divided by 0.45 plus 1 plus 0.1, as we did before. And this was equal to, let me recall it, let me do it, have it done by ear. This is equal to 0.81. So my degree of belief that the coin is fair decreases, but is still high. Now, how can we do it numerically? Well, we can do the following stuff. I can set like I don't know a number of uh, k of repetitions. I can like first draw a parameter p with some probability. So I draw this parameter p. It can be either 1 or 1/2. So it will be one 1/2 plus 1/2 times a binomial, a Bernoulli random variable uh, of parameter uh, 0.1. So this will give me p equal to 1/2 with probability 0.9. So this I am extracting. I am extracting p as my prior with the same probabilities as my prior. I'm sampling p. Then what I do? Well, then I sample, I toss a coin with probability p. So it is a Bernoulli random variable of parameter p. And this will be my coin toss. And I repeat this procedure many times. So let me do it many times. Uh, Precisely, let me do it one 10,000 times, say. Then I bind these two data frames and I will see what I have. Um, so now you see P is equal to Z to not to 0. How is it possible? It should be equal to sorry, let me. No, it's equal either to 1 or 0.5. Most of the times, approximately 0.9 times of the total, it will be 0.5. And 1% of in 10% of the cases, it will be 1. And the contours is always 1. I don't understand why. So probably I will do it in with a 4 cycle. Sorry for that. So for in one k point to say is equal, and then I have to initialize the vector, so coin toss is equal to vector of what mod is equal to numerical, and the length is equal to k. That should be so the mod of the vector has to be equal to numerical, but cannot let's put double, and let's see what happens. Okay, now it's I got this data frame. Now, well, so this data is drawn accordingly of my, I mean, the first column is drawn accordingly to my prior. Now I observe that ahead, so I only take the rows in which the coin toss is equal to 1. So I take my framework and I filter it where coin toss is equal to 1, and then I mutate with count, and if is equal, no, so I don't remember the function mutate very well. I mean, this is a basic function, but you always need to look at it. So mutate x equal to count, and I have to count the number of the number of, no, I have to summarize. Uh, have to count so let me see. Well, I can simply count. So there are 900, 9,019 uh, elements with p equal to 0.5, and so now it seems to confirm the fact that, okay, let me take a bigger k and do exactly the same procedure. So no, I'm not really. Ah, okay, because here I'm not doing coin toss equal to one. Doesn't make sense. Okay, okay, now it's better. I have 45,000. 45,124 divided by k is the proportion of p which are equal to 0.5, and uh, mm, and so yes, I have to. You see, now I have in this. I save this data frame into like this posterior variable, and now I will go and work directly in the console, which is better. So what did I do now? I've taken only the outputs that I actually observe. Sorry, that I actually observe. So posterior, I have filtered only uh, the variables where the coin toss gave me head, and 45,000 of them were given in the case where p is equal to 0.5, while almost 10,000 when p is equal to 1. Well, now I can like do the proportion of them, like and it will give me like the posterior, like there are for I can do the mean of the column, like yes, I should do the mean actually. So let me do it directly here instead of saving into the sorry, not the mean, but have to take to select the variable second variable, which is p, and sorry, which is n, the count, okay, and divide it by k. And divide it by the sum of okay, and they have 81 divided by 18, which were exactly 0.45 divided by 0.45 plus 0.1. This was exactly, so you see, this is a method to sample from sample from the posterior after I observe the method to sample from the posterior. I do many samples and then I generate data according to my prior and keep only the data that is in line, that is in favor, does not contradict my observation. The function BRM works similarly. It generates many of the beta zeros zero, beta 1, and beta 2. And then, according to the normal distribution, sorry, to the prior distribution, and then keeps only those for which for which the data which makes sense in the expression pitch equal to beta 0 plus beta 1 di gender plus beta 2 di eh, eh, di context. Uh, where the data is the one that I give the observation. So in this way, the RMS, the RAM is able to sample from the posterior. Of course, I didn't say precisely what does this word make sense mean. So we actually don't know how this algorithm works, but the idea is this one. Once we make precise this sentence here, which makes sense in the expression. But you see, once we sample from the prior, knowing we can select the sample to get a sample from the posterior, and this is really useful. So this was what I wanted to tell you about this uh, this stuff. So thank you for the